Hi students, in the last classes we learned the HCF by using the Euclid division lemma. Today we have to discuss some more examples of to finding the HCF by using the Euclid division lemma. Let us take an example 65 and 125. Okay students, 65 and 125, these two are positive integers. We have to take 125 is greater than 65. Okay, 125 is equal to, we have to divide from 65. 65 into 65, how many is the 125? 65 ones are, if you take means 65. If you take twos are 230. 130 is greater than 125. We cannot take 65 ones are we should get plus. How many remainder? 65 ones are 65. We should subtract it from 125. So 125 minus of 65. What will be the remainder? 5 minus of 5 0. 12 minus of 6 60. So the remainder is 60. Here r is not equal to 0. I told in the last classes when the r is equal to 0, we have to stop this process. When r is not equal to 0, we have to continue this process. Here r is not equal to 0. I am continuing this process. Again apply the EDL for 65 and 60. 65 it is equal to 60 into 1s again 60 ones are 60. So here 65 is there. So remainder is 5. 60 ones are 60. 65 minus of 60. This product we have to subtract it from 65. 65 minus of 60 is remainder is 5. Then again r is not equal to 0. Again apply the EDL for 60 and 5. 60 is equal to 5 into 12. 12 5 is 60. Again remainder is equal to 0. 60 minus of 60 is equal to 0. So therefore remainder is equal to 0. Therefore r is equal to 0. We have to stop this process. Therefore HCF is equal to HCF of 65 and 125 is the last divisor is 5. This format is in the form of A is equal to BQ plus R. This format A is equal to BQ plus R. The last divisor, the last value of B is the HCF. Next, I will take another example. 375 and 550. 375 and 550. 375 and 550. Okay students, 375 and 550. 550 is greater than 375. 550 is greater than 375. So using the ideal, so 550 is equal to 375. We have to divide it from 375 for the 550. 375 into 1s I should take. If you take 2s, it become more than 550. 750 is become. It will not go. So 1s I should take. Remainder how much? 550 minus of 375. We should subtract it. 550 minus of 375. 375 ones are 375. This product we have to subtract it from 550. So 10 minus of 5, 5. Here 4. 14 minus of 7, 7. Here 4. 4 minus of 3, 1. 175 is become. 175 is the remainder. Again r is equal not equal to 0. R is not equal to 0. If we should continue this process, again apply the EDL for 375 and 175. So 375 is equal to 175 into 175. 1s are 175. 175 2s are if you take, how much become? 175 into 2. 2 5s are 10, carry 1, 2 7s are 14 plus 1 15, carry 1, 2 1s are 2 plus 1 3. 350 is become. Here 375, okay, it will come. So 2s I should take. 375 2s are how much? 350. You should subtract it from 375. 375 minus of 350, it will become 25. So again r is not equal to 0. Again apply the EDL for 125 and 25. So 175 it is equal to 25 into 25. 7s are 170. 25 7s are 175. The remainder has become 0. Therefore, we should stop this process. Therefore, the HCF is the last divisor what? 25. Yes, HCF is 25. So like this we have to find the HCF by using the Euclid division lemma. Okay students, and 225 and 315 is there. You have to take the homework for doing at home. Next I will go to the directly we should go to the exercise problems. Okay students, open your textbook. Exercise 8.1 is there. In the first main, we have to find the HCF by using the EDM. You have to solve in your homework, in your notebook. I will go to the next question. Second questions. Second question, what is there? Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. Q is some integers. Okay students. Any positive odd integers. I will take A and B. Any positive integers. A and B are any positive integers. Here in the general form of EDL, A is equal to BQ plus R. Then what is that? Any positive odd integer is in the form of 6q plus 1, 6q plus 3, 6q plus 5. Here A is equal to 6q plus R, where R is greater than or equal to 0, less than B. Here R is equal to less than or greater than or equal to 0. So what is that? R less than B. B value what is there? Here B is equal to 6. Here R value what? R is equal to less than B. Less than B means 0 to 5. So 0, 1, 2, 3, 4 and 5. We cannot take 6 because of 6 is equal to 6. Because of R is not equal to B. R is less than B. So therefore we should take only 0 to 5 is the remainder. Okay students, A can exist, A can equal to, it can be exist 6q plus 1, 6q or 6q plus 2 or 6q plus 3. So 6q plus 0 we should take 0 after 1, after 2 and 6 or 6q plus 3 or 6q plus 4 or 6q plus 5. So A can exist these kinds of values. Q is some integers. In the questions they are told that Q is some integers. Q is quotient. So A is equal to, A is not equal to, A is not equal to 6q plus 0, 6q plus 2 or 6 and 6q plus 4, because these are even integers, even positive integers. In the questions, any positive odd integers is in the form of 6q plus 1, 6q plus 3, 6q plus 5. But 6q plus 0, 6q plus 2, 6q plus 4 cannot exist because of 0, 2, 4 are the even integers. Therefore, A can only exist for A is equal to 6q plus 1, 6 or 6q plus 1, so 2, so 3 and 6q plus 5. So, hence the proof. For example, we should take any positive odd integers. I am taking 7. We should divide it from 6 because of B value. This is A and this is B. B, this is quotient and this is the remainder. So I am taking B value how much? 6. So I am writing the divisor. So 7, any positive odd integers, 6, 1s are 6. What will you get? 1 is the remainder. So 7 equal to, that means A equal to 6 into 1. 6 into 1 means 6 into Q. Plus remainder what? 1. This is the remainder. So 6q plus 1. 6q plus, this is the remainder of 1. So we can take any positive odd integer, we should divide it from 6. But we should take dividend more than 6. More than 6. That's all. So A is equal to 6q plus 1. We should take any another one example. 21 we should take. I am divided from 6. 6 3s are 18. What will you get? 3. Again 21 is equal to 6 into q plus remainder what? 3. 6q plus 3. So these are positive odd integers. You can take any positive odd integers is in the form of 6q plus 1, 6q plus 3 and 6q plus 5. That's all students. So next question. Question number 3. An army next. Okay. Should we go to the next question? Question number 3. An army contingent of 660 members is to march behind an army band of 32 members. Okay, students. One army is there. So one of the two groups are there. One group is 660 members and another group is 32 members. These 660 members are the march past group and the 32 members are the bandset groups. These two groups are there in the two groups are to march in the same number of columns. Same number of columns. They are marching the same number of columns. 660 members from group and 32 members from groups. These two groups are marching the same number of columns. What we calculate? What is the maximum number of columns in which they can march? These two groups can march in the same number of columns. What is the maximum number of columns? That number we have to calculate. So this maximum word is indicated to HCF of these two numbers. What is that? 616 and 32. So 616 and 32. First, the two groups are. One is 616. This group is the mass pass group and 32. This group is the bandset groups. These two groups can march in the same number of columns. So we have to calculate 616 and 32. We have to calculate the HCF. So 616 here greater than the 32. So 616 it is equal to 32 into. So 32 how many is the 616? So I am taking 32 into 19 I am taking. So 19 into 38, carry 3, 13 3 is 57, 57, 19 3 is 57, 57 plus 3, 60, 608 is become. So 608 and 616. So is nearly to become. So I am taking 19 how much? 608. We should subtract it from 616. 616 minus 608, it becomes 8. So 8 is the remainder. Here r is not equal to 0. Again continue this process. Again apply the integral for 32 and 8. So 32 it is equal to 32 is equal to 8 into 8 4 is 32. So again remainder is become 0. Remainder is become 0. Therefore the last divisor is the HCF. So the HCF of these two numbers is 8. Therefore, what we calculate? What is the maximum number of columns in which they can march? It means there are 8 columns they can march in the march, these two groups. Next, okay students. Next question, number 4. Use EDL, means Euclid division lemma, to show that the square of any positive integers is either of the form 3m or 3m plus 1. Okay students, you can take any positive integers, any square, the positive square integers. I will take, let us say x is equal to 9q plus 1 or 9q plus 2. 3q. Here 3m plus 1 is there now. So therefore 3q plus 1 and 3q plus 2 you should take. So these positive integers is in the form of 3q plus 1 and 3q plus 2. This number you should square it. Square the any positive integers. I will take positive integers. These are the positive integers. is in the form of 3q plus 1 and 3q plus 2. So these numbers we have to do the square. So I will take, let us take x is equal to 3q. First one, x is equal to 3q. So we have to square it on both sides. So x square is equal to through 3q whole square. So 3q whole square means 3 into q into q. 3 we should divide multiply by 2 times and q is also multiplied by 2 times. So 3 into q into q, 3q square. Because 3 into 3q square instead of I will write m, where m is equal to, m is some integers, I will take 3q square. You should take any, give the any value of q, you will get that x value. This is x square. So you should take any positive integers, you have to do the square. If you square these numbers, this form is become 3m. I will take 3q plus 1. X is equal to 3q plus 1. So again squaring on both sides. So x square is equal to 3q plus 1 whole square. So this is in the form of a plus b whole square. That means 3q whole square, a square, plus b square means 1 square, plus 2 into a means 3q into b means 1. A square plus b square plus 2ab. Next, 3q whole square means 9q square. 3 square means 9, q square means q square, plus 1 square means 1. 2 3s are 6q. So I will take 9q square and 6q. I will take the one root and plus 1 is the other root. So I will take out the common factor. I will take 3, only 3. So remaining is 3. 3 3s are 9. Q square is there, no? Q square as it is we should write down, plus 3 6 is there, 3 2s are 6. Q is as it is we should write down, plus remainder is 1. So here 3 into 3q square plus of 2q is the form of m. The value should be a m. I will take in general because of m is some integers. In the question they are told that m is some integers. So integer means this value is indicated as m. So therefore m is equal to 3q square plus 2q. So hence the proof. So I will take one example of students. Here 16 I will take. Here 3q plus 1, 3q plus 2 is there, no? So here a is equal to bq plus r. Here b is equal to what? 3. Means b is the divisor, 3 is the divisor. So I will take any positive squaring numbers. So I will take 16. 16 is the perfect squaring numbers. So I will divide it from 3 because of b value is 3. 3, how many is 16? 3 5 is 15. So remainder is what? 1. So here 3. This is what? Q. 3q. 16 is equal to, that means a is equal to 3 into q plus remainder is 1. 3q plus 1. See here, 3q plus 1. So in another example, 9 we should take. 3. 3 3s are 9. What will you get? 0. That means what? 3. 9 is equal to 3 into q. This is q.
Storage.
3q plus 0. Okay students. So next this is the proof. That's all. So next question. The last question, 5th question. Use EDL. The next question, use Euclid division lemma to show that the cube of any positive integers is of the form 9m, 9m plus 1, 9m plus 8. Same as it is. Here squaring, here cubing. Okay students, let us take xb. Any positive integers, I will take 9m, 9m plus 1, 9m plus 8 is there. So x can exist 9m or 9m plus 1, 9m plus 2, or 9m plus 3, 9m plus 4, and 9m plus 5, 9m plus 6, 9m plus 7, 9m plus 8, 9m plus 8, that's all. Okay, here x can any positive integers. These in the form of, I will take q. M instead of, I will take q. Q is some integers. Because of, I will show that 9m, 9m plus 1, 9m plus 8 only. Therefore, I will take means m instead of q. Okay, let us take one example. X is equal to 9q. Here, cubing on both sides. Because of, use the idiom to show that cube of any positive integers. So, I will do the cube of both sides. So, x cube it is equal to 9q. 9q whole cube. So 9q whole cube means 9 into 9 into q square, q cube. 9 into q cube. So here 9 into 9 is 81 q cube. So 9. So this value is instead of m. So m is some integers. M is equal to 81 cube. So you should take any positive or positive integers. You have to divide cubing on both sides. You will get 9m plus 4, 9m 4. Next, another 9m x is equal to 9m plus 1. I will take 9 cube plus 1. I will take again cubing on both sides. So x cube is equal to 9 cube plus 1 whole cube. Here a plus b whole cube format. A plus b whole cube. So what is the a plus b whole cube? A cube plus b cube plus 3ab into a plus b. Okay. So here this is a and this is b. A cube means 9 cube plus b cube means 1 cube plus 3 into a means 9 cube and b means 1 and a plus b means 9 cube plus 1. Next, 9 cube whole cube means 9 into 81 cube. See here, 9 into 81 cube. Same. I will write that. Plus 1 cube means 1 because of, and then 3 into 3 9 is 27 cube into 9 cube plus 1. So 9 into 81 cube plus 1 plus 27 into 9. You should multiply that. 27 into 9. What will you get? 9 7 is 63, 6 carry, 9 2 is 18, 18 plus 6, 24, 243 is become 243 q into q square plus 27 q into 1, 27 q. Okay students, next, this I am making the group these two terms. One I am not making that group, I will except one. So I will take the 9 is the common factor. So remaining is 81 cube plus here 243 is there. I will take the already 9 is the common factor. You should divide from the 9. 9 2 is 18. Remaining is 663 is become 9 7 is 63 q square plus 9 3 is 27 3 q. So lastly finally plus 1. I will not make in the group for plus 1. So next, x cube is equal to here 9